Okay, so this talk will be a bit more theoretical and definitional. And I will talk about how do we define adaptive security for garbling schemes. And this is joint work with Estuardo, Chris, Ifla, and Sabina. Okay, before we get to that, let's recap what garbling is and how you would use it for MPC. So we have two parties, Eva and Gabriel. And Gabriel will do the garbling. The way they do this is first they hard code their input into the circuit and then do the garbling. Here's some syntax. We call C tilde the garble circuit. D is sometimes called the decoder or the output map. And for the rest of the talk, I will assume that C tilde includes D or the output map. And K is, if you know Yao's garbling scheme, think of those as just the wire labels. All right, so Gabriel sends the garble circuit in the offline phase, and only later adaptively Eva chooses an input to be garbled. Eva does this and gets their garbled input using an oblivious transfer protocol only in the online phase, and now they have all the information they need to evaluate the garbled circuit. Okay, so how do we define security? And this, as Rahul pointed out, was first introduced or defined formally by Belare Huang and Rogaway in sort of a simulation style, which seemed natural at the time because the selective security of gambling schemes is defined in this style. So why not also the adaptive security? So in the real game, of course, the adversary chooses the circuit first, gets the garble circuit, and then later chooses X. And we say that this should be indistinguishable from an ideal game where an efficient simulator produces the garble circuit, only given the topology, like that's what phi of C means, and then later seeing the output of the circuit evaluated with X, it produces a garbled input. All right. So crucially, we call the size of X tilde the online complexity. And we want X tilde to be small, that is, that it grows with the size of the plain input. Why is this important? Well, if we didn't have a requirement on the online complexity, then we could have just sent C tilde in the online phase, and then the online complexity would grow with the circuit size, which we don't want. We also don't want things to grow with the output size. But actually, this is inherent in the SIM definition. So we have this lower bound by Applebaum, Ishai, Kushilevitz, and Waters. They showed that basically, if you want to garble any circuit, then you can't get rid of this dependency in the output length as well. And then later, Fupachek and Wicks sort of generalized this to any kind of pseudo-random circuit, or if you know any circuit with pseudo-entropy. So the main difficulty is SIM allows the adversary to both choose the circuit and choose the input. And this is a sort of over-approximation of security. And for example, if you chose the circuit to be a pseudo-random generator and the input to be a seed, then any PPT simulator is going to have a very difficult time ensuring correctness. That means C tilde X tilde equals C of X with high probability. All right. So one may weaken the simulation definition and see if that is more feasible. And BHR also defines this. And I won't talk too much about this, but this is natural sort of indistinguishability type definition. Here you need that C0 X0 equals C1 X1. So you have the strong requirement that they coincide in the output. And that seems a bit restrictive if we want to garble cryptographic circuits like the ones we saw in the counter example of the lower bound. So we want to introduce now our definition. via modification of the standard simulation definition. All right, so the first thing that's very important is we don't want to allow the adversary to choose the entire circuit. So the circuit now comes instead from a sampler. The sampler produces C as well as some leakage of C, which again I denote phi of C. And then O, which is some oracle that sort of models the cryptographic guarantee of the circuit. I'll explain what that is in a moment. So think of C as just the circuit with like your key or whatever randomness hard-coded. The leakage is just like the circuit without the secret embedded. And then this oracle could be like, for example, the ACPA insecurity with the circuit exchange. Think of it as maybe an AES circuit that you want to garble. And then the circuit should be cryptographic. What does that mean? And I might also use the term output indistinguishable or output secure somewhere in this code. It means that C, when evaluated on the adversarial input, is indistinguishable by any efficient distinguisher to C evaluated on all zeros of the same length. All right. Okay, so we remove that, and now we give the circuit to the adversary. And here we relax the correctness requirement. You don't always need the simulator to get the output of the function in order to produce a garbled input. For example, if the circuit it provides a pseudo-random guarantee, then it actually does not need to know anything to produce a pseudo-random output. And again, I'd like to emphasize that we can do this because the adversary here does not get the key embedded inside the circuit because it doesn't choose all of the input. All right, so this is our definition. And now I need to show you that it's actually useful. So here's an application. Suppose that you'd like to encrypt some data on a database, and you store that the key you used to do the encryption on some device. What if the device gets corrupted? Okay, so the solution is to secret share the key, store it on 2 devices, store the shares on 2 devices, and then do a so-called dice protocol to compute via MPC the ciphertext. All right. And here's the protocol. And I want to use our DSIM definition to do that. And let's describe what the security experiment is. So first thing in purple is basically all of the secret shares being sampled, and then the encryption circuit along with those shares embedded. Think of this as being outputted by the sampler. And now, if B equals 0, then honestly garble, otherwise simulate it. Give the necessary information to the adversary, but now the adversary also knows K2, which is their share. And to garble the input, either do it honestly or simulate it, give it to the adversary. Okay. Now, to model sort of concurrency, we also provide the adversary with an encryption oracle, so it can get ciphertexts under the key K1 plus K2. All right, so how do we prove this? Proof sketch. First, when you want to use DSIM, you really need to prove that the sampler is out secure or cryptographic. So the way you do this is to show that currently the view of the adversary is this thing on top. It's indistinguishable from what you have in bottom. And you basically observe that this thing I've highlighted is as good as basically making an additional oracle call. For those of you who pay a bit more attention, you'll notice that we actually need to reduce to a stronger property because the adversary has a key share and can query the oracle on related keys. All right. So now we actually can apply our DSIM assumption. We replace, okay, this is the real game with B equals 0. Now we replace things with simulated things via DSIM. and we're still not done yet. We need to replace kind of the oracle now and make it blue, which is when p is equal to 1. We again reduce to the NCPA property. All right, so just to show you that you can actually build distributed symmetric encryption using PC. Hold on. Yeah, but this global simulator is actually your pizza simulator in disguise. All right. So the paper actually contains other results, which I did not get to talk about. First one is bootstrapping. So if you have DSIM for NC0, which is the class of Boolean circuits of constant depth, then you actually get DSIM for 10 of those circuits. And this is nice because DSIM actually preserves the online complexity. So if you could do DSIM, shallow circuits, with online complexity that's say big O of X, big O of size of X, then you could also do the same thing for poly circuits. And that would overcome kind of the barrier you have for simulation definition. But this is a conditional result. So we actually don't know yet if we can build DSIM for NC0.
Great.
The idea here is actually quite interesting. You garble kind of a garbling scheme, hence the term bootstrapping. And you can do that because the K, the big K, into your wire labels remain hidden inside the circuit when we garble DSIM. Okay. Okay. Another nice result we have in the paper is a more direct result, a direct proof of the lower bound of Huber checks and wicks, specifically for garbling schemes, and small improvements of other people's constructions by observing like things that they don't need. So it's like, I've not put this here, but like Jaffa Gullis, Tafura, and Wicks showed the constructions in, so NC1, when they needed somewhat pivotal encryption, but you actually don't need it. So yeah, I would recommend taking a look at the paper because it's a sort of survey of many different things in the kind of area of adaptive security for garbling schemes. That's all. Thank you. Happy to take questions.